All right, so now, my friends, we're going to rerun all this, right? Because we're basically done. And so to run all this again, we're going to first upload the dataset because it is not yet uploaded in the notebook. So upload, and then make sure to find your whole machine learning dataset folder containing all the codes and datasets. So then we're going to go inside, then we're going to go to part 3, classification, and then k nearest neighbors, KNN, and then Python, and then we select our social network ads dataset. Click open. Now it's going to be uploaded on the notebook. Perfect. And there we go. Now we can run everything. And to do this, well, we're going to click runtime here and then simply run all. And let's just start from here. Okay, great. Our k nearest neighbors classifier was created and trained properly. And at the end, so all the predictions are generated again. We can actually have a look at them. And wow, we seem to have some great predictions. That's, remember, on the test set. So all this is correct. Here we have an incorrect prediction, meaning that the KNN predicted this particular customer to buy the SUV, whereas in reality, that customer didn't buy the SUV. Then all this is correct, all correct, all correct. It seems really good. Here we have another incorrect prediction, this time the opposite one. Our model predicted that this particular customer didn't buy the SUV, whereas in reality, that customer bought the SUV. All right, correct, all correct, all correct. So pretty good. Wow, I think we actually have very, very few incorrect predictions. Let's actually check it out right now. Okay, no, so I didn't see it properly, but we actually have in total 4 + 3 incorrect predictions. That's really, really good. That's better than the logistic regression model. Remember, we had actually an accuracy of the test set of 89%. So here clearly the k nearest neighbors did better than the logistic regression model, and you will perfectly understand why when I show you the visualization. So it's actually here. All right, so 4 + 3 = 7 incorrect predictions, then 64 correct predictions of the class 0, meaning 64 correct predictions that the customer doesn't buy the SUV, and 29 correct predictions of the class 1, meaning 29 correct predictions that the customer buys the SUV. And then we have indeed 4 incorrect predictions of the class 1, meaning 4 incorrect predictions that the customer buys the SUV, and 3 incorrect predictions of the class 0, meaning 3 incorrect predictions that the customer doesn't buy the SUV. So very, very good. And now, as you can see, it is still executing the cell that plots that 2D array, showing all the prediction regions and prediction boundary of the KNN model, first on the training set and then on the test set. And the reason why it is taking some time here to execute, oh, there you go, we are at perfect timing, is simply because, the KNN model is actually very compute intensive. There are a lot of computations when running the KNN model, and that's why it took some time. And so now let's interpret the results. So remember, with the logistic regression classifier, the prediction boundary was a straight line. And that's because the logistic regression model is a linear classifier. We'll actually see another type of linear classifier in this part. But remember, for linear classifiers, the prediction boundary or prediction curve for classification is a straight line. And in 3 dimensions, it's a straight plan. And in n dimension, it's a straight hyperplane. And so here we had a straight line, which therefore resulted in having a lot of incorrect predictions, because as we can see, there are a lot of green points here, green customers who bought the SUV in reality that fall in the red region, where we predict indeed that the customers don't buy the SUV. And same for these ones here, here we have a lot of customers who in reality bought the SUV, but were predicted not to because they fall in the red region. And so what we were hoping for is to build a new classifier for which the decision boundary, separating the 2 prediction regions, does something like this, would not be a straight line, but some kind of a curve catching all the red points here without catching those green points here and here, okay? So that's what we were hoping for, and well, that's exactly what we got here. Thanks to our KNN model, we don't get a smooth curve, but we get actually some kind of a curve that indeed catches all the red points here without catching the green points and leaving those green points and these ones inside the green region, where they should end up, right? And of course, here we have some green points that were super hard to catch because they are stuck in the middle of all those red points here, so that's fine. And anyway, in machine learning, we want to avoid Overfitting, when we have some too perfect predictions on the training set and therefore probably resulting in having bad performance, bad predictions on the test set. And well, speaking of the test set, let's see how our KNN did. It should be fine now. Yes, it is executed. And once again, we get excellent results, right? Because same, the KNN prediction curve or prediction boundary or even decision boundary catches all the right customers, the red customers who didn't buy in reality the SUV, therefore leaving the green customers who bought in reality the SUV in the right prediction region, the green region. All right, so that's already much better, and indeed, we increased the accuracy of the test set by 4%. And now the question is, can we do even better than this? Well, that's exactly what we're going to find out in the next practical activities to discover the big winner. And until then, enjoy machine learning.